Today I'm going to be solving proposition 2.6, and it starts out with, if a straight line be bisected and a straight line be added to it in a straight line, the rectangle contained by the whole with the added straight line together with the square on the half is equal to the square on the straight line made up of the half and the added straight line. So reading it kind of doesn't make any sense. So I am going to try to explain it better using the givens and what I'm proving, and then drawing my picture later on will definitely help you try to piece together the pieces. So for right now, what Euclid gives us is, he gives us this line AB, and he bisects it at C. And so using that and the definition for bisecting, we can then say that AC is equal to CB. And then he also says that this line AB is is extended to this point D. And D is however long you want to make it. It's easier if you make D shorter, so that's what I did. And so we're trying to prove this. So we're trying to prove that this line AB times BD plus CB squared, so two of these, is equal to CD squared, so two of these lines. And it of course makes more sense once my picture's drawn and I start doing stuff. So first step of doing this construction is to make this square CDEF, and you can use that using proposition 146. And 146 says that you can make a square using a straight line. Also, the straight line used for this would be CD. So now that we have that, I'm going to create my square. And it might not be perfect, but it's okay. CD and EF. So now we have that. So the next thing we're going to do is we are going to connect two points, and that would be I would be connecting DE, and that would be using postulate 2. And postulate 2 says that if you have two points, then you can connect them using a line. So we'll be using that. So we have that now. So the next thing we're going to be doing is we are going to be using proposition 1.31, so 131, and that basically lets you create parallel lines from a point. So the first one we're going to be creating is a line, I believe it's BG, and BG is going to be parallel to DF, or I guess CE, either one, because it's a square and so both sides are parallel. So I'm going to be using CE actually. And so I created that line using point B. So then we're going to label this point right there H, just so we have a little name for it. And then out of point H, what we're going to do is we are going to create another set of parallel lines. They're going to be called KM, and they're going to be parallel to AD. So KM is parallel to AD, and that is out of point H, like I just said. And it's for the same reason. Okay, so we're going to create that real quick. Okay. So the next thing is we're going to create another set of lines. And this point right there, we're going to name it L. Whenever 2 points or 2 lines cross, usually name them. Okay, so we're going to create AK, and they're going to be parallel to CL. And so that will be from point A. So we're going to finally just connect those. And now our construction is done. We're pretty much done making the picture. Now we're just going to prove what we've already said right here. So the first thing we're going to say is that, oh yeah, we're going to restate something. So right here, we're just going to say the AC is equal to BC. You don't have to add this, it just makes more sense if you know that already, that that's true. So because AC is equal to BC, and these two quadrilaterals are in the same parallels of KM and AD, then that means that this figure, AL, is equal to this figure, CH. So we're going to say that. So we're going to say that this figure, AL, is equal to this figure, CH. So we said that. And that uses proposition 136. And it really just says what I just said. Equal bases, same parallels, the figures are equal. So now that we have that, we are going to say, we're going to now see what this is equal to. So CH is equal to this figure HF. And it's equal to that because the components of a parallelogram about the diameter make these parallelograms equal. So because diameter DE cuts this square, then these two components equal one another. And that is proposition 43, which says that. Okay. So now, using these two steps, we see that there's a common denominator, it's CH, and so we can then equal, or AL is equal to HF, because these are common, and so you can use combination 1, which says that if two things are equal to one thing, then they are also equal to one another. So we have that. So now we are going to add something to both of these. We are going to add this chunk right here. We're going to add CM to both. So it's this figure right here, and it would be this figure right there that connected to make this larger figure CM. So we're going to add both to both sides. So whenever we write that out, AL plus CM, if you combine them, that would then make AM, this whole figure. So then you can just say AM is equal to, so now that we're on the other side, this is where it kind of gets tricky. So you have this figure, and then you have this figure right there, and they're added. But they are not a, like square or anything, or a rectangle like that is. And so we're gonna name it a gnomon. And so it would be this figure right here. Euclid names this gnomon NOP, so we're going to do the exact same thing. And so he basically says that HF plus CM equals NOP. And so that would be combination 2. And that basically says if equals be added to equals, then the remainder, or it's whatever, then the product is equal. I really just name blanked. So now that we have that, we are then going to take apart AM and figure out what makes AM. So we're going to set AM equal to something. And if we look at this, AM is this huge thing. And so we can, it's kind of like finding the area, I would say, where two sides multiplied by each other is equal to the whole area. So I could say that this side AD, which if you look at the whole figure, it's AD KM, so that times, I guess you could call this figure AK, would equal AM. But Euclid kind of takes this a step further, okay? And he says that AK can also be equal to DM because of the parallelness of it and just how it's set up. So AK is equal to DM. But here's the tricky thing, DM is also equal to BD. And so based on that, we can say that, we've already said that AD would be one of the sides. Well, then we can say that BD is the other side, kind of. So this would be the area of AM in a sense. And I kind of used a mixture of common notion 4 and common notion 1 to deduce this. Common notion 4 says that things that coincide with each other equal one another, or equal each other. And then common notion 1 says that, I've already kind of stated it, but if two things are equal to the same thing, then they therefore are also equal to one another. So now we have that. We can then plug this back into this, and we can say that AD times BD is equal to this shape NOP. And that would be common notion 1, which I just said previously. So there's that. Okay, so now that we have that, we are going to add another thing into this equation. So we haven't even touched this figure LG, so we're going to add LG to both sides of this. So plus LG. Okay, so that would also be common notion 2, why we're adding LGN. If you add equals to equals, the remainders are equal. So based on this, you're going to basically keep this the same. So AD times BD plus LG is equal to, okay, so this is where things change. NOP is this figure plus this figure plus this figure. Well, we just added this figure. So now we have all the 4 components that make up this larger CF, which is this whole figure right there. So we can then say that that is all equal to CF. We're just simplifying basically. So the next step is trying to figure out what LG and CF actually are. And we've already found this, so it's not easy. It's easy to deduce what's about to happen. So LG, like the area thing, I'm gonna write it down here. LG is, if you try to find the area of that, you would say that it would be LH, so all of this times LE, all of that. But again, LE is equal to LH. So it would be 2 LH's, so LH squared equals LG. But Euclid again takes it a step further. He says LH is equal to CB. And so if it's LH squared, then it's also CB squared. So we're gonna say that. So LG equals CB squared. Okay, so then try to find that CF, this large thing. So if you look at it again, CF. So it would be, let me get rid of this real quick. So again, it would be CD, and then it would be this side DF. So CD times DF, well, again, DF is equal to CD. So CD times CD, CD squared. You can say CD squared. So then we just found that using just our picture and deducing what these mean. So then you can say that AD times BD plus this newfound CB squared is equal to CF, which is the newfound CD squared. So you can do that now. CD squared. And so I used combination 1 for this. I've said that already quite a while, so I don't know. And basically, we got to the end of it. We found that this whole figure is equal to this whole figure, all of those. So we did it, QED. So two things equal one another, or if two things equal something, then those. I really can't use this one. I really can't use this one. Then, yeah, QED. Okay, now I'm gonna recreate this on the